Hello and welcome to Compassion. Today we are going to begin with NMR spectroscopy, and in this particular video we are going to learn about basic principles of NMR spectroscopy, what is nuclear spin, and what is chemical shift, what are different factors affecting chemical shift values. So let's begin with the basic principle. So NMR spectroscopy, which stands for nuclear magnetic resonance, it involves absorption or irradiation of the molecule with radio frequency waves. And these radio frequency waves are generally having lower frequency and lower energy. So when any molecule is irradiated with radio frequency wave, it causes nuclear spin transition. That means we need a molecule or a nuclei which is having some nuclear spin. So NMR is generally used for finding out organic structure, and it allows to detect atomic nuclei and tells us its environment within the molecule. So as I said that a nucleus having a nuclear spin can be detected by NMR spectroscopy. So what kind of nucleus can have nuclear spin? So if a nucleus is having odd atomic mass or odd atomic number or both, then it is said to have some nuclear spin. For example, if I take 1H1 proton, so its atomic number as well as atomic mass is odd. Similarly, 3H1, 15N7. So these are few examples of nuclei whose spin is half integer and they are having odd atomic number as well as odd mass number. That means they have nuclear spin. If I consider C13, O17, then their atomic number is even, but their atomic mass is odd. So their spin is again half integer. Similarly, if I take 2H1, that is deuterium, so its atomic mass is even, but atomic number is odd. So this can also be detected. Its uh, spin is integer. And if a nuclei is having both even atomic number as well as even atomic mass, then this spin number is 0. So these cannot be detected in NMR spectra. For example, 12C6, 16O8. So here their atomic number, atomic mass both are even. So their value is 0. So it is very important that the nucleus must have either atomic mass or atomic number that is odd, or both should be odd. Only then they can be detected in NMR spectroscopy. So simplest example of a nuclei having nuclear spin is a proton. So right now we are going to talk about 1H1, that is a proton whose atomic number as well as atomic mass is odd. So this odd atomic number implies that it has got some spin. If I place these proton under the influence of some external magnetic field, then these spinning proton generally they start generating their own magnetic field, which is called as magnetic moment. So when there is no applied magnetic field, then these protons spins in all direction and there is no energy difference. As soon as we start applying magnetic field, then the protons they start aligning themselves either with the magnetic field or against the magnetic field. So when a proton aligns itself with the magnetic field, as you can see, this spinning proton direction and the direction of external magnetic field, they are pointing in same direction. So it is aligning itself with the magnetic field. So that state is lower energy state and it is called as alpha spin state. And when a proton aligns itself against the magnetic field, that is the direction opposite with respect to the external magnetic field, then that is called as beta spin state, which is having higher energy. So we get two energy states, lower energy state or alpha spin state and higher energy state called as beta spin state. The energy difference between these two spin state is denoted by delta E. So When we say that nucleus is in resonance, that means when a nucleus is irradiated with some radio frequency photons having energy equal to delta E, that is the energy difference between the two spin state. We have to apply that much amount of energy, only then we can say that the nucleus is in resonance. If the energy is less than this delta E value, that means nucleus will not be in resonance. So under these conditions, when we apply delta E amount of energy, then the proton which is in alpha spin state, they can absorb the photon and then they flip into the beta spin state. Now let's see what is magnetic shielding. So effective magnetic field, that means how much amount of magnetic field is actually effective in NMR or in spinning of the nucleus, is denoted by B effective, which is equal to external magnetic field minus the shielding magnetic field. So let's see a naked proton. Generally, protons are surrounded by electrons. So if we say the proton is naked with it is not surrounded by electrons, then if we apply 70,459 Gauss of magnetic field, then that much amount of magnetic field will be absorbed by this proton because it is naked. But generally protons are surrounded by electrons, and these electrons, which in this picture is denoted by this blue color, they partially shield these protons. So electrons, they generally circulate and they generate their own induced magnetic field, and this induced magnetic field opposes the external magnetic field. So if I apply same amount of magnetic field, that is 70,459 Gauss, to a shielded proton which is shielded by the electrons, then the proton will feel less than 70,459 Gauss of magnetic field because it is shielded by the electrons. So in that case, there won't be any effect. The result is that magnetic field at the nucleus is weaker than the external magnetic field, and then we say that the nucleus is shielded. If we apply magnetic field which is slightly stronger than that, so earlier we applied magnetic field of 70,459, now we are applying magnetic field of 70,460. So in this case, the stronger applied field compensates for the shielding, and the proton can absorb the energy or effective field of 70,459. So we say that the effective magnetic field at the shielded proton is always weaker than the external magnetic field. So the applied field must be increased for resonance to occur at a given frequency. That means we can summarize that we have to apply stronger magnetic field or the magnetic field which is greater than the effective field. Only then the proton will be in resonance. If we apply lesser magnetic field, then it will not be in resonance. Now, what is this shielding and de-shielding? Let's see the example of methanol. So, if we see methyl alcohol, it is having two sets of proton. So what is this two sets of proton? The protons which are present attached to this carbon atom, there are three protons, CH3. Their surrounding is same, their chemical environment is same. So these three protons are chemically equivalent. But if I consider the proton attached to oxygen atom, it is attached to oxygen. So its surrounding is totally different from remaining three protons. So here we say that we have two sets of protons. Now let's see which proton is shielded and which is de-shielded. Oxygen, the proton which is attached to oxygen atom, this is less shielded. Why? Because this oxygen is more electronegative. Since it is more electronegative, what is going to happen? It is going to pull the electron density towards itself, due to which the proton becomes less shielded and hence it absorbs at a lower magnetic field. We consider the remaining three protons which are attached to carbon atom, they are more shielded. Why? Because carbon is less electronegative, so it cannot pull whole electron density of three protons towards itself. That means these three protons are still more shielded, and hence we'll have to apply higher magnetic field, so it absorbs at a higher field. So the protons attached to carbon atom, they are shielded, and the proton which is attached to oxygen atom, that is de-shielded. Now where does these shielded and de-shielded proton show signal or appear in NMR spectra? So this is the NMR spectra of methyl alcohol. The protons, these blue color protons, they are more shielded, and this pink proton which is attached to oxygen atom is more de-shielded. So always more shielded protons will be higher field, they will have higher magnetic field values, so they will be upfield, that is they will be closer to TMS. TMS is the reference which we use. This I will explain in my incoming video. More shielded protons, they appear at lower field, or we call it as down field. So shielded protons will be near TMS, while de-shielded proton will be away from TMS, which is used as a reference in NMR spectra. Now let's see what is this chemical shift. So the variation in the position of NMR absorption arising from electronic shielding and de-shielding, as I explained that more shielded protons are towards TMS, and less shielded protons are away from TMS. So why there is variation in the position? So that is due to shielding and de-shielding, and that is called as chemical shifts. So the difference in ppm, parts per million, between the resonance frequency of proton being observed and that of the TMS, that is tetramethylsilane, which is used as a reference, that is called as chemical shift. So we can have machines of different frequency like 60 megahertz, 100 megahertz, 300 megahertz machine. For same compound, they will give same chemical shift values. So this is the formula for chemical shift in ppm, which is generally chemical shift is denoted by delta. So it is shift downfield from TMS in hertz divided by total spectrometer frequency in megahertz. So as I said, whether we use instrument 300 megahertz instruments or 100 megahertz instrument or 600 megahertz, their chemical shift value will be same. The only difference is that the spectra will become more and more clear, but the value remains same. These are few important chemical shift value. This I have got it from Claydon reference book. So if you want to check these value for solving the problems, if you need these values, then you can refer that reference book, or you can pause this video and take the screenshot. So these are the values. Here you need to remember three basic values, like methyl. For methyl, the value is 0.9, or you can say delta 1 approximately. For methylene protons 1.3, and for methine proton it is 1.4. For remaining functional group, the values we can calculate the values depending upon what kind of proton is what kind of element is attached, whether it is more electronegative or less electronegative. So if we have methyl ketone, then for methyl ketone it is 2.1. For acetylenic proton it is 2.5. If some halogen is attached to methylene, CH2, so for methylene we have the value 1.3, but when halogen is attached, then the value increases due to inductive effect, which is in the range of 3 to 4. If some unsaturation is present like vinylic proton, then the range is 5 to 6. For allylic proton, the range is 1.7. For aromatic ring, we have the value in the range of 7.2. Similarly, for aldehyde, you will always get a signal in the range of 9 to 10. For carboxylic acid, between 10 to 12. If we have alcohols or amines, then the value is variable between 2 to 5. for phenols 4 to 7, and for amines 1.5 to 4. So these are few values which are beneficial for solving the problems based on NMR. This is the range, you can see this is the chemical shift value from 0 to 10.5 or more than that. Tetramethyl silane is taken as the reference whose value is considered as 0, and with respect to this TMS we have different chemical shift value depending upon what kind of functional groups we have. If we have completely saturated molecule which is not next to oxygen atom like methyl, methylene, methine, then the value is between 0 to 3. If these methyl, methylene, methine groups are attached to oxygen atom, then the value is between 3 to 4.5. This is due to electronegativity of oxygen atom. When a proton is present on unsaturated carbons like alkenes, then it is between 4.5 to 6.5. If you have some aromatic compound, then we get peaks in the range of 6.5 to 8.5. And if we have carboxylic acids or aldehydes, ketones, then the values are greater than 8.5. So the chemical shift of methyl group in alkane, as I said, is 0.9. So if we talk about methanol oxygen, so methanol is CH3, CH2, CH3OH. So here this CH3 is attached to oxygen atom. That means its value is going to shift to 2.5 due to electronegative oxygen atom. So it will be de-shielded due to electronegativity of oxygen atom. So as the electronegativity of groups or elements increases, the chemical shift value or de-shielding will also increase. So here is the example. As I said that for methyl the value is 0.9 ppm. But when to this methyl group, if some electronegative atom or group is attached, then what is going to happen? So we can see if fluorine is attached, which is the highest electronegative atom in the periodic table, whose electronegativity is 4. So the chemical shift value is increasing from 0.9 to 4.3 ppm. If OH group is attached, so oxygen is electronegative but less electronegative than fluorine. So its value is going to shift towards 3.4 ppm. Fluorine's electronegativity is lesser than oxygen atom. So the chemical shift value of CH3Cl will be 3. For bromine, it will be 2.7, and when iodine is attached, then the value is 2.2. So here we can see as the electronegativity of the element attached to methyl group decreases, its chemical shift value also decreases. So that is the effect of electronegativity on chemical shift. The next factor is anisotropic effect, which is really important. So here we are going to understand different groups. So let's see double bonds or aromatic rings. So when we talk about double bond or aromatic ring, that means pi electrons are present. So these rings produce larger de-shielding effects on their vinylic or aromatic protons. So here you can see this is the direction where we are applying the external magnetic field, and here we can consider this is our aromatic or vinylic proton. So when the electrons are in circulation, so they are going to generate their own magnetic field. So here we can see that there is induced field which reinforces the external field, that is de-shielding takes place. So in between where we have pi electron density, you can see the direction of arrow. It is going in opposite direction with respect to the direction of external magnetic field. That means they are opposing each other. That means there is de-shielding, the value is going to increase. That is the reason that when we have aromatic ring or some pi electrons, then their chemical shift values are higher. So let's see the example of benzene ring. So this is benzene ring. We are going to apply external magnetic field in this particular direction. In benzene we have upper circular electron cloud and lower circular electron cloud, and these circulating electrons, they generate their own ring current or induced magnetic field. This is the induced magnetic field. So when we see the direction of these induced magnetic field inside over here, then it is opposite with respect to the external magnetic field. But when we see these protons, then here they are aligned with the magnetic field. So at the center of the ring, the induced field acts opposite to the external field, and these induced field lines curve around, but on the edges of the ring or outside of the ring, these induced fields adds to the external field, and this causes the deshielding. The aromatic protons are strongly deshielded, which results in larger chemical shift value, and that range is between 7 to 10 ppm. Let's see anisotropic effect in aldehydic protons. So when we see aldehydic protons, we have carbon-oxygen double bond. This is the direction where we are applying the external magnetic field. And we have pi electron cloud, which produces their own magnetic field or induced magnetic field. This is the proton which we are talking about. So over here, uh, the deshielding of aldehydic proton will take place. So aldehydic proton is deshielded by the pi electron, pi electron clouds or pi bonds. So this is also deshielded by the electron withdrawing effect of the carbonyl group. So we have carbon oxygen double bond. They are going to pull the electron density towards itself from this particular proton, and due to this its chemical shift value increases, which is between 9 to 10, and whether it will be near 9 or near 10, that depends upon whether we have aliphatic aldehyde or aromatic aldehyde. So here also similar to aromatic ring, the value increases, that is there is deshielding. Let's see acetylenic proton. So in case of acetylenic proton, we can consider acetylene as a cylindrical shape. It is linear structure. So we have carbon-carbon triple bond. So over here, it is partially shielded by a triple bond. Instead of de-shielding, there is shielding over here. So when the acetylenic triple bond is aligned with the magnetic field, then the cylinder of the electrons, they circulate to create the induced magnetic field. So over here, this is the proton which we are talking about. So here they are opposing. The acetylenic proton lies along the axis of the field and it opposes the external magnetic field. This is in opposite direction like this. So since they are opposing, so there it will be more of shielded. Its value will be between 2 to 3 ppm for acetylenic proton. So this anisotropic effect is generally observed in aromatic rings, aldehydes or acetylenes, and depending upon whether there is shielding, whether the proton is shielded or deshielded, the value increases or decreases. What is the effect of hydrogen bonding on the protons? So when we have hydrogen bonded protons, so uh, let's see example of alcohols or amines. So chemical shifts of OH protons in alcohols and NH protons in amines, that depends on the concentration. As I told you that for alcohols and amines, the value is variable between 2 to 4. This variation in value is due to hydrogen bonding. So if we consider highly concentrated solution, then these protons are generally OH or NH protons are de-shielded due to hydrogen bonding. So they will absorb at a lower field of delta 3.5 for amines and 4.5 for alcohols. If alcohol or amine is diluted with some non-hydrogen bonding solvent, then in that case hydrogen bonding doesn't play any important role, and in dilute solution their value is observed around delta 2, which is lesser as compared with hydrogen bonded molecule. So hydrogen bonding and proton exchange, that accompanies, they may contribute to broadening of the peak in case of these protons. So generally the signal for alcohol or for amines, they are generally broad due to hydrogen bonding as well as proton exchange. So if a broad peak appears because proton exchange from one molecule to another during the NMR resonance. So this was all about basics of NMR spectroscopy. In next video, I will be explaining you how to interpret NMR spectra, how to find out how many signals will appear in NMR spectra for a particular molecule. So thank you so much. Please like, share and subscribe.